Alright, hi guys. Today we're going to be discussing neural networks, especially in the context of machine learning. And just before I get started, all the uncited images in this lecture are either from Wikipedia or lectures from TJ Machine Learning Club that are also on neural networks. And the examples in this lecture are also from past TJML lectures, and these lectures were drafted by previous TJ students Nikhil Sardana and Vinay Baib. If you're interested in exploring neural networks further after this lecture, I'd highly recommend attending several of the sessions that we're going to be having in the club over the next several weeks, where we'll go into greater depth on how neural networks work and how to code your own and some of the more theoretical aspects of these models. Here we're going to basically do a high level overview of the different parts of how a neural network works and how to train a neural network for different tasks. So yeah, let's get started. Okay, so an introduction to artificial neural networks. So over the past couple weeks, we've been discussing like a lot of like the low level like ways to mathematically represent neuron firing and how to better understand that. This is sort of stepping a little bit away from that, at least for the time being, and we're going to be exploring a machine learning model that's actually it's basically a high level abstraction of how neurons work in our own brain. So this relates to neuroscience in two ways. One, basically, the original formulation of artificial neural networks was actually made by neuroscientists, right? I mean, neural networks are, as the name suggests, based on the neural networks in our own brain. While there are many, many differences, and the artificial neural networks that are responsible for a lot of the advances in machine learning, these are very different from biological neurons. But the when you view it from a high level of abstraction, they are essentially they perform similar computations, right? So in the sense that neuroscience inspired these models, that's one way that these machine learning models are related to neuroscience. Another way that these models are related to neuroscience is actually, especially over the past several years, these networks have been applied to understand a lot of neuroscience related problems. For example, actually, this was a project done at TJ by a student who graduated, but the student basically created neural networks to analyze fMRI images of people with Alzheimer's. So then, in the future, given some new fMRI image, then the neural network could actually predict whether or not the person who was scanned with this fMRI had Alzheimer's or not. And so it's sort of a two-way street here between like machine learning and neuroscience, um, uh, right? And the second way is how these are related is that the neural networks actually help us better understand um, stuff that's going on in our own brain by allowing us to do like better image processing and image classification. And so we're most likely going to be discussing applications of neural networks to understand disease, brain disease, and possibly other different topics related to neural networks in the future. So this primer should hopefully set you up for that. Um, okay, so as I mentioned before, machine learning model artificial neural network is a machine learning model that is basically a high level abstraction of the neurons in our own brain. So it does not exactly copy what happens with individual neurons, but the overall operation is similar. Some interesting facts. It's been proven that given a sufficiently large network of neurons, you can represent any function, any sort of mathematical function. Um, and basically we train these neural networks using a process called backpropagation. And given enough training data, so these are examples of what we are trying to do. So these can be like images or voice samples or basically anything. we can essentially train this neural network to approximate any function. And if you're familiar with the term deep learning and stuff, many people think it's like a buzzword, but it's actually a field of research that has been fueled by progress with artificial neural networks. Deep meaning the number of layers of neurons that we have in our network. And so basically in this lecture, we're going to explore how neural networks work and get a high-level overview of how we can train neural networks for our own tasks. So before we go on to that, some basic history. Artificial neural networks have actually been around since the 1940s, and it actually was sort of originated from the labs of neuroscientists, not computer scientists. And these neuroscientists were basically trying to approximate how the brain works computationally, right? And so this is just as I mentioned before, this is just an example of how studying neuroscience can actually improve or accelerate our progress in fields like AI, where we're trying to emulate, at least to a certain extent, what's happening in our own brains. But unfortunately, neural networks weren't always popular since they were created. Actually, around the 1980s, during something called the AI winter, there was actually an active sort of discrimination against researchers who were into neural network research, because at that point, neural networks were actually very bad at doing stuff, performing tasks, right? And that was mainly due to the lack of computational resources that were available at the time and the lack of data to train these networks. But as we've increased our computational power over the past several decades, and also collected lots more data on a bunch of different tasks like images, we've seen a dramatic increase in the effectiveness and overall popularity of neural networks. The sort of breakthrough moment that a lot of researchers in the field point to is the something called the AlexNet paper, which was released in, I believe, 2012. And this basically outperformed all previous algorithms on something called the ImageNet dataset competition, or the ImageNet competition. And the ImageNet competition is basically, the dataset consists of thousands of categories of different images like dogs, cars, ships, etc. And the goal is, given a certain image, we want to predict what category that image is, right? Which category that belongs to. And so neural networks were very, very good at this. They sort of surpassed all other sort of approaches by a significant margin. And since then, many people have been interested in understanding neural networks and applying them to problems. So to start off, we first have to explain like what a neural network is. So a neural network is basically a collection of individual units called neurons, and these neurons are connected, as shown below, where the neurons in one layer are connected to every single neuron in the other layer. And basically, we can have sort of many layers like this. Here, there's only one hidden layer and one output layer, but you could imagine that we actually extend this to have multiple layers, and then finally result in an output layer. And basically, we provide some sort of input to our neural network here, and as we push the input through our network, we eventually arrive at some output. And this input can basically be anything. The popular sort of example that is used is, or that I'm going to use in this lecture, is image data, but it can be anything. It can be information related to stock prices, and then the output is basically a prediction of some stock price. It can be sequence data, and you're trying to predict what is being spoken. Although there's different models for that. There's sort of advanced architectures for those kind of tasks, but the a sort of easy to understand application of this is images, and so that's what I'm going to talk about here. You can imagine that when you have an image, it's sort of a grid of pixels, right? So you can imagine that if you unroll the matrix of pixels and then feed each pixel value into the input, and then the vector is basically contains a spot for every single pixel in the image, then you can imagine that once you have that, the output could be, if we were trying to solve the ImageNet competition, it could be one output that represents the category of what we were trying to predict, like the category of what was in the image, right? So imagine if we have a picture of a dog, we take each pixel value, put it into a large vector, and then the output is some sort of number that represents the category dog. And so that's essentially, I know here we have like two output nodes, but for the dog example, you'd have more. But basically, neural networks can be used to approximate any sort of function. And so the individual unit behind neural networks are these things called neurons, where you have some inputs, and then these are going to be numbers, right? You have to represent your data numerically somehow. For the example of images, we would convert each, we take the pixel values, which are just numbers between 0 and 255, and then we pass that in here, right? And for every input, we multiply that input with some sort of weight, and this is just some number, right? And we sum these up, add a bias term, and then once we have this number, we apply a nonlinearity function to it, and then we get our output. So the weights are just numbers, right? These are just it could be like 1.2 or something, and the bias is also just some scalar value. It's just some number, and so we basically perform this like weighted sum where the weights are W1, W2, and Wn. We add this bias here, and then we push it through a nonlinearity function, which I'm going to discuss on the next slide. The reason why we apply this bias here, it's basically, I mean, if you think about a line, if you don't have a bias, it's all the lines, regardless of what the slope of the line is, they will always go through the origin, right? And so by not having a bias, you sort of restrict the amount of complexity you are able to, like the possible complexity of the function that you're trying to represent. So by adding this bias term, you essentially allow it to represent more complex functions. And the same is true with the nonlinearity function, which I'm going to discuss soon. And so, you can imagine that this this whole sort of set of operations represents one circle here, right? So in this circle, what happens is all of the numerical inputs from this node, and this node all get passed in. They get multiplied by some weights, right? Where this is W1, this is W2, and this is Wn. You sum them up, add a bias, push it through some nonlinearity function, which I'm going to discuss, and then out it goes to the nodes, the neurons in the following layer, which it is connected to. Okay. So the nonlinearity functions are included in the neuron for the same reason that the bias is included. Basically, if you don't have a nonlinearity function, the span of different functions that you can represent is limited, right? What ends up happening is if you don't have this function, if you don't push these values through a nonlinearity function, the whole set of operations can just be condensed to one sort of linear operation. So regardless of how many layers you end up adding to your network, it can all just be condensed through pushing. All that operation can be condensed to having just one neuron, right? So basically, having these nonlinearity functions allows your neural network to learn nonlinear mappings from your input to your output, right? And there's different possible nonlinearity functions. You can have a sigmoid function that looks like this, a ReLU function, which is just 0 and then the max of 0 and your x value, or the hyperbolic tangent function. And so having this nonlinearity function allows your network to learn more complex mappings from your input to your output. Okay, so hopefully the stuff on the previous two slides made sense. This is sort of just formalizing what we did on the past two slides mathematically. So here, N3 represents the output of neuron 3, N4 represents the output of neuron 4, and then N5 represents the output of neuron 5, and then N6 represents the output of neuron 6. So basically, what we're doing here is multiplying whatever value was in neuron 1, or this is like the first number in our input, we multiply that value with W13, which is connecting neuron 1 to neuron 3, right? And then we do the same thing for the value in neuron 2 and multiply it with its corresponding weight W23, right? This connection. And we do a similar thing for all the neurons in this layer. And then finally, for calculating the value of N6, we just do the same thing, making sure to add our bias terms throughout, and we push it through some nonlinearity function. Here, we're using the sigmoid function. And then we have our output, right? So this is essentially, given some input and given the proper weights, we're going to talk about how to learn these weights soon, but given these learned weights, how do you go from your input on one side of your neural network to the output on the other side, right? This is how you do it. So in practice, though, the equations that I showed on the previous slide aren't actually used to perform the computations. What actually happens is we sort of package all of the weights of our neural network into matrices. And the advantage of putting everything into matrices is that we essentially allow for our computations to be sped up by parallel computing capabilities, especially with GPUs. So graphics processing units, which are like pretty popular for gaming, these are very good. These components of computers are very good at performing lots and lots of matrix multiplications. So if we can formalize our forward propagation steps in terms of matrix multiplication, we end up having a drastic speed up in the speed it takes for forward propagation. Okay, so before we go into that, just reviewing, or if you don't know, this is how you multiply matrices, right? So if you have one matrix, which is just a way to like organize numbers, and then another matrix, what you do is multiply every row in the first matrix with every column in the second matrix, and that goes into your output matrix here. And then you do the same thing. So what this actually means is you do 1 times 7 plus 2 times 9 plus 3 times 11, and the resulting value is 58. Then you would do 1 times 8, 2 times 10, and 3 times 12, and that resulting value would go here. And you do the same thing for this row and this column, and that would go here. And then this row and this column, which would go here. And so you can't multiply any two matrices together. The dimensions have to match in the sense that, so if matrix 1 has dimensions A and B, where A is the number of rows and B is the number of columns, and then matrix 2 has the dimensions B and C, where B is the number of rows and C is the number of columns, then you can do it, right? If this matches with this, then you can multiply two matrices, and then the resulting dimensions of the final matrix are A, C. So here we go, right? So here for matrix 1, A would be 2 because we have 2 rows, and then we have 3 columns, so B would be 3. And then for matrix 2, B would be, the first dimension is a number of rows, so that would be 3, and then the number of columns is 2. So A here is 2, B is 3, and C is 2. So then our final dimensions are going to be 2 and 2, and that's what ends up happening here. So that's essentially the basics of matrix multiplication. So now that we know matrix multiplication, we can actually express our forward propagation steps in terms of matrices, right? So if we collect all of the weights in our neural network for this layer as follows, where each column represents a neuron in the previous layer, and each row represents a neuron in the current layer, then we can just multiply the outputs of the previous layer with our weight matrices, add the biases to this resulting product, and then after pushing it through our sigmoid function, so this is basically an element-wise sigmoid. So for every element in our resulting vector, once we perform all of this, we just calculate the sigmoid, and then we get our new outputs for the last layer. We get our new outputs for this layer, sorry, and then we can perform those same steps again for the following layer. And so more generally, we can express the forward propagation steps like this, where in order to get the outputs for the next layer, the inputs for the next layer, we multiply the current weight matrix with the current inputs, add the bias terms, and then push it through a nonlinearity function like so. And then, expressing things with matrices, as I mentioned before, drastically speeds up the computation speed when you're using GPUs. Okay, so now we know once we have our trained weights, how do we push an input through a neural network and then get output, right? But the the question that hopefully you're asking is, how do we know the weights in the first place, right? And so in order to do that, we first have to find a way to um, measure how well our neural network is doing on some task, right? And so to do that, we introduce error functions or loss functions. So, what specific loss function you use depends on the specific task you're performing. So if you were doing some sort of regression task where, for example, given some properties of some company as your input, you're trying to predict stock price as an output, what you would use for that would be like mean squared error, which is shown here. If you're doing some sort of classification task where you're trying to predict if some image is a cat or a dog, or if it's a picture of a brain and does the brain have Alzheimer's or not, then you'd use binary cross entropy, or these are just two examples, and there's many different types of loss functions. But having loss functions like these basically tell us how bad our neural network is currently doing. And so once we have this loss function, our goal would be to minimize the loss or the error, right? We essentially want to make the error go down, and that means improvement in performance. So now we have to figure out, okay, how can we decrease the loss? So we're gonna conduct a process called gradient descent. But before we do that, I just want to explain derivatives. Um, so derivatives basically specify the rate of change of some function with respect to some variable of that function. In the two-dimensional case where you have one input variable and one output variable, basically one notation for derivatives is this, and um, basically a derivative says, okay, if I change the x value by some amount, how much is the corresponding change in y? So for lines like this, the derivative is always constant. It's for example, it's just the slope, right? So for this function here, the derivative is 2, and so we basically say that if you change x by some amount, then the resulting change in y will be twice that amount. And so if you take the partial derivative, the derivative of x squared, you get 2x. And so what this means is if you draw the tangent line to this graph at some point x comma y, then the slope of that tangent line is going to be equal to 2 times the x coordinate of the point that you plot, right? So, for example, if you drew a tangent line where at x equal at the point 1, 1, right? So you can imagine that the line would go like this. Then um, the slope of the tangent line would be 2 times x, or 2 times 1, so 2. So this basically means that depending on what the x-coordinate of the point that you're drawing the tangent line to, the slope of that tangent line changes. Whereas here, the tangent line slope is always 2, if that makes sense. But we can also do partial derivatives, right? So if we have multivariable functions where the output variable is dependent upon several variables, and not just x, if we have multiple variables, then partial derivatives basically tell us, okay, with respect to this single variable, how much is our output value changing, right? And so we can think about this visually as taking a slice of our graph and then sort of tracing the function that gets sort of projected onto that slice, and then just calculating the single derivative there. And what this amounts to, like mathematically, is holding all the other variables constant while modifying this variable a little bit, and then seeing the corresponding change in the output. And so partial derivatives basically tell us how the output of some multivariable function is changing with respect to a single variable. Okay. Now we're going to introduce the concepts of gradients. So gradients are basically the collection of partial derivatives for all variables for some function, right? So what this vector actually represents is if you're on a function, imagine like this is like a hill, right? And when you're sitting at this point on the graph, the gradient actually tells you the direction of steepest ascent. So it tells you what direction to move all of your variables in order to most rapidly increase the output of your function. And so if you sort of connect this to the ideas that we were talking before about losses, or like loss functions or error functions, our goal here is to minimize the error, right? So if we think about the loss function as being a function that inputs all of our weights and biases, all these values that we're trying to learn, and then the output is this loss, then we can actually calculate, like if we can calculate the gradient of the loss with respect to all of the parameters of our neural network, which are all the weights and biases, then we can just move all the weights and biases in the direction opposite to the gradient. So since the gradient is the direction of steepest descent, the gradient tells us, okay, how should I adjust all the weights and biases to increase the loss function the fastest? Obviously, that's not really helpful because loss is a bad thing that we're trying to reduce, right? So we just take the direction opposite to the gradient, or negative. We just negate the gradient and then move all of the variables of our neural network, all of the parameters, in the direction opposite to the gradient. Okay, so now since after and one thing is there's actually like a reason why there's a proof of why the gradient vector is actually the direction of steepest ascent. I'm not going to go into that here, but if you take multi, you'll learn about that. Okay, so now that we know about gradients, we can specify what gradient descent is, which is the main sort of learning algorithm that we train neural networks with, or it's the most basic one, and there's variations of it. So what we do is we keep computing the gradient of our error function with respect to the weights and biases, which are the parameters of our neural network, right? And as I mentioned before, the gradient actually tells us so how should we adjust the weights and biases of our network to increase the loss function. But if we take the negative of the gradient, then it tells us how to decrease the loss function, right? And so this is basically telling us, okay, how do we adjust our weights and biases to most effectively improve the performance of our neural network on whatever task we're performing, right? And so gradient descent, we repeatedly compute this gradient and then adjust all of the weights and biases in the direction specified by the negative of the gradient. And we keep doing this until the gradient that we calculate is lower than the magnitude of that vector is lower than some threshold. And that basically means that we arrive in some sort of minimum, some local minimum, where it's sort of flat and we're not going up or down with our network, right? So basically this allows us to minimize our loss function. Here we actually are showing like an animation of gradient descent where we're adjusting theta 0 and theta 1, which are parameters of some model, and this is the loss function. In reality, it's sort of hard to create graphs like this because even in the simple neural network that we were showing on previous slides, there's way more than two parameters. And so, this is a three-dimensional graph, and that's basically the highest amount of dimensions that we humans can visualize, all right? So if you have a neural network with maybe like 1,000 different parameters, 1,000 different weights and biases, then it becomes very hard to plot this sort of loss function graph. Um, so it's sort of hard to visualize what happens with more complex neural networks, but the overall sort of intuition that you gain from this animation is the same. Okay, one thing to note with gradient descent though is that there is a chance that you get stuck in some local minimum. If you've taken calc, or I think math pre-calc as well, you know that there are local minimums in functions where you arrive at some sort of flat point in your graph, but that's not actually the least value that your function can take. And in this graph we show many different sort of local minimums. And so that is always a risk. For example, in this gradient descent animation, you could get stuck here or here. It's sort of by luck almost that you came and converged over here. So that's always a risk, but usually gradient descent results in pretty good performance. One question you may be asking is, why don't we just find the global minimum? In BC or AB, you actually learn techniques to calculate the global minimum for some functions, but this is actually very hard to do with large large multivariable functions with neural networks. As I was saying, you can have neural networks that have 1,000 dimensions, like 1,000 different parameters. And so finding the global minimum of a function that depends on that many variables can be quite challenging. So that's why we use iterative processes like gradient descent. And so one question you may be asking is, okay, how do we actually get the gradients? Basically, you can think about the loss function as a composite function of all the different weights and parameters of our neural network, where it's basically a composite function that is iterative, where like the output of this node depends on all of the inputs that were coming in, and so on, right? And so when you're performing backpropagation, this is essentially an efficient way to calculate the gradients for your neural network. And I'm not going to go too much into the specifics here in this lecture, but what essentially ends up happening is you repeatedly use the chain rule to calculate the individual partial derivatives for each weight and bias. So you learn how to change that individual weight and bias to increase or decrease the error most effectively. And basically, the reason why you call it backpropagation rather than forward propagation is once you calculate the output of your neural network for some input, what you end up doing is iteratively moving backwards through the network. So you calculate like the the partial derivatives for all of these weights and biases first, and then you move backwards and then do this and then backwards and so on. So that's why it's called backpropagation. It basically occurs in the direction opposite to your forward propagation. And so what ends up happening is once we have all those gradients, we can perform a step of gradient descent like I was mentioning on the previous slide. Okay, that's basically all for this lecture. Thank you for listening.